Our first speaker is Manas Kulkarni. He'll talk about nonlinear Schrodinger equation.
Thank you. I thank all the organizers for giving me this opportunity. It's been a great week. So today I'm going to speak about nonlinear Schrodinger equation, its connection with nonlinear fluctuating hydrodynamics and KPZ universality class. So most of what I speak about is the work done in collaboration with David Hughes and Herbert Spohn, and some older work with Austin Lamacraft. So after we heard the pedagogical lectures by Herbert Spohn, in this talk I'm going to try to connect those things with nonlinear Schrodinger equation as the main example. And before this, I'm going to start with motivating why nonlinear Schrodinger equation as a specific example. What are nice properties of nonlinear Schrodinger equation, and also it goes by the name Gross-Pitavsky equation. And then I'm going to just present some brute force numerics, some molecular dynamic simulations of discrete nonlinear Schrodinger equation, with no reference to fluctuating hydrodynamics or KPZ. And then from the results we get from those numerics, we'll try to understand why we are getting KPZ exponents, and then try to strengthen the connection with the KPZ. So as two main examples were shown in the previous talks, namely anharmonic chains and discrete nonlinear Schrodinger equation. So nonlinear Schrodinger equation has some large amount of features which is often missed in other models. I'll just try to outline a few of them. So first of all, so this is basically just the nonlinear Schrodinger equation, continuum nonlinear Schrodinger equation, a complex differential equation, and this is its Hamiltonian structure. So what are the special things? So one thing is, if you discretize this equation, you get a discrete nonlinear Schrodinger equation, which I call DNLS. And DNLS is non-integrable. And this is going to be the place where I'm going to stay most. So I study discrete nonlinear Schrodinger equation, and so I study a generically non-integrable system, and fluctuating hydrodynamics, as we know, is true for generic non-integrable systems. So we are going to discuss mostly the discrete nonlinear Schrodinger equation, the non-integrable version. Nonetheless, there is a nice discretization which makes it integrable even in the lattice version. So I'm not going to address this, but there's some nice recent work on this. So there is some limits where you get integrable discrete models, non-integrable discrete models, and so on. Another thing is, there are physical realizations of what we call vector NLS, so many coupled nonlinear equations, which means that you might end up realizing some coupled KPZ or coupled fluctuating hydrodynamics realizations. So I will speak about this a little at the end of my talk. And one also has realizations of two-dimensional versions of nonlinear Schrodinger equation, two space dimensions. So these are physically realized examples. So there are experimental realizations in cold atoms and nonlinear optics, not only in terms of the model, but also in terms of some techniques available to measure things in this model. So this is another motivation to use this system as a platform to study KPZ physics or nonlinear fluctuating hydrodynamics, in addition to the Fermi-Pasta-Ulum chains and so on. There is a further extension of this model, which is called gain-loss NLS. So there's a modification of this model where it loses its Hermitian structure. So you have non-Hermitian nonlinear Schrodinger equation, so which doesn't have a Hamiltonian structure. So question is, what happens in this kind of non-Hamiltonian systems? So this can be a nice example to study those kind of physics also. As I will talk as I will explain, this model also has fairly rich regimes where there's a high temperature regime which is diffusive, and then there's the intermediate temperature regime which is KPZ-like, and so they are like temperature regimes where there are some effective additional conserved quantities that start appearing, which is not true in other models, and so this is a good example to study such rich properties. 2 years back, Ablowitz and Muslimani wrote down a non-local version of nonlinear Schrodinger equation. So there's a non-local version of nonlinear Schrodinger equation which is integrable, and which is lattice integrable, and which is lattice non-integrable. So there are discrete versions of this which is non-integrable, there are discrete versions of this which is integrable, and there's a continuum version which is integrable. So you have a non-local one-dimensional system which has all these properties. So there are basically very few non-local integrable models that we know. So there's a lot to do in trying to find non-local analogs of this equation. Okay, so since we already had the pedagogical lectures, let me jump right into what we are interested in calculating. So what I'm interested in calculating is essentially a Fourier transform of what Herbert wrote in his lectures. So basically these are density-density correlations, but instead of studying it in x and t space, I'm just going to study it in k omega. So this is called dynamical structure factor, and this just measures dynamical density fluctuations in the system. So it's basically the same quantity as we have been used to in the last 2 days, just Fourier transform of it. The main point is that linearized hydrodynamics or linearized fluctuating hydrodynamics fails to describe long wavelengths, and this is where you need to understand the role of nonlinearity in a very systematic manner, or do brute force numerics to understand the role of nonlinearities. So this is the only quantity of interest for this talk. So that is the thing, and this is just a motivational slide to show that such kind of experiments are actually feasible in cold atoms, where they can actually measure this kind of dynamical structure factor using something called variant of Bragg's spectroscopy. It's not done yet in the regime we are interested, so this is just a motivational slide that is just to remind us that the S of k omega is physically measurable in principle. So, okay, so the focus is going to be discrete version of nonlinear Schrodinger equation. So the first thing is I'm going to describe exact Hamiltonian numerics. This is basically just brute force numerics, and we'll try to calculate some exponents associated with this model by exact numerics. Then we will try to see what to expect from mapping to 1D fluid and scaling. So what kind of exponents you would expect. And the third thing is we will establish a connection with nonlinear fluctuating hydrodynamics and KPZ. So this is the plan. This work on discrete nonlinear Schrodinger equation was first started by brute force exact numerics. So I will try to tell you the chronological story of this. So we started with discrete nonlinear Schrodinger equation and calculated it in brute force method, and then okay. So then let's so this is the discrete 1D discrete NLS. And this is what it is. So it's just complex psi fields on a lattice, non-integrable, and there is a inherent lattice spacing. If you take the lattice spacing to 0, it becomes integrable. Okay. Now the evolution of this is the equation of discrete nonlinear Schrodinger equation, which this is lattice Laplacian. So the way this is evolved, the way this is evolved is you first evolve it partially in momentum space and then partially in real space. This is just a minor detail, but it is very useful to know that there is this method called leapfrog method and Fourier split method. I think most of you know this, where you simulate this. There are many ways to simulate this. This is just a complex partial differential equation, right? So, complex differential equation. So, but there is this most effective way to simulate it, where you evolve it partially in momentum space and partially in real space, and then you go back and forth, back and forth. Okay? The interesting thing about this is that the error that you accumulate in time is very high derivatives in space. Okay, so the error you accumulate in time is very high derivatives in space, meaning that you'll have terms like this. Something like this, just an example. So this is the errors that you accumulate, and this in fourth derivatives of k is like k power 4. Okay, so the errors you accumulate is much higher than k to the 3/2. So since we expect k to the 3/2, these errors that you accumulate here are sort of irrelevant. So that is why this method is very useful for studying dynamical structure factor. Okay, so if you want to study just soliton dynamics or shock waves, you don't need to use this method. So this is the so by rho and theta, I just mean we'll come to this. So I just mean rewriting this complex function as square root of rho e to the I theta. So any questions? Yeah.
If you apply this topical numerically,
yeah,
you get two operators nu tau over 2 sequentially.
Yes.
It doesn't seem to make much sense. Why don't you just make it into one operator nu of tau?
Okay. So this is right. So actually I think it boils down to one operator in tau, and this basically boils down to one operator in tau and this. I think so. So this is basically, I think this additional discretization probably doesn't.
And at the beginning and the end.
Right. So this is equally good. This will also generate errors only which are higher orders in spatial derivatives. Okay?
This one here is a little bit nicer because it means at the point you stop after one interval, you actually have time reversal. You have a reversible dynamic.
Yeah.
Whereas this one is not, if you do it in reverse, it's not the same problem.
No, that's true.
So that's just it's just a detail.
But it only makes a difference at the two ends.
Exactly.
Right.
It's
Okay.
more that there's a nice time point about which you have time reversal invariance.
Okay. So now a word on initial conditions. So the initial conditions. So basically from here we calculate this correlation function. So this is the flow chart. One word, and this is the first kind of simulations that we did with Lamarcraft, with Austin Lamarcraft, and there we use these initial conditions. So these initial conditions, we just call it near thermal. So basically these initial conditions are drawn from a thermal distribution of the quadratic Hamiltonian. So these are not perfectly thermal initial conditions, but and this is where the temperature enters. So these, but our claim was that it should be reasonably independent of initial conditions, because if you evolve it for a long time, it should more or less reach some steady state. And so this was the claim that DNLS equilibrates fairly rapidly, and it should not depend on choice of initial conditions. And this is basically what we claimed in 2013 and sort of remained it as a claim in 2015. But recently Herbert and Christian Mendel, they showed that it is indeed true. So even if you use the right e to the minus beta h, you get the same thing. So which means that DNLS is sufficiently chaotic. But so what to expect? So question is, so when we were doing this work with Austin, we sort of expected 3/2, meaning we expected, so let me just say what I mean by 3/2. Okay, this width should scale as k to the 3/2. So we expected this, and the reason we expected is is for mainly two things. At the same time, there was a PRL by Henk, which said that a generic non-integrable 1D classical Hamiltonian with short-range interactions should fall into KPZ class. So the statement is that any generic, I mean there are some exceptions, but those are, I'll not get into that, but any generic non-integrable 1D classical Hamiltonian with short-range interaction should fall into KPZ class. That is one reason you should expect 3/2. I mean, and there are several other reasons, because we would expect a discrete nonlinear Schrodinger in 1D to behave like a classical 1D fluid. And classical 1D fluids are known to have some anomalous behavior in low dimensions. So it is expected to show some anomalous behavior. So that is, yeah.
So the second statement you made seems clearer, but the first one, can you explain what you mean by false in the
So I'll try to explain, and I think Henk will correct it. So the statement is that all the correlation functions, like these S of k omega and so on, for these generic classical 1D systems, will behave like correlation functions of the KPZ system.
Now the S of k of omega and the generic, you're talking about
Equilibrium correlation functions, yeah.
Somehow KPZ is supposed to be this prototypical non-equilibrium.
No, I mean you calculate, for example, I mean.
That's what's surprising about it. Equilibrium time correlation. It's dynamic correlation to equilibrium. But they're dynamic.
Yes.
So, yeah. So I think in this PRL, the correlation functions were of the form of Prahofer-Spons correlation functions of KPZ. I think that is, and there are some, and the exponents were also KPZ. So that was. So, yeah.
Next conjecture, which is possible. Quantum mechanical systems will have the same generic behavior as classical ones.
Yes, that is basically, yeah. So there is no, to my understanding, there is no numerics also to show that yet. So, but yeah. So I'm talking about just classical systems here.
This would be at low enough temperature in a gas system or gas system? The second conjecture.
Okay. Okay. So basically, this is what we saw. This is the first set of data that came up in 2013, and this is basically the structure factor which I was showing here. This is for 3 different wave numbers, and they all have a collapsing form. They collapse into this, and yeah. Right, and we see this half width which is going as k to the 3/2. So we see this. So basically we saw evidence of the exponent by brute force numerics with no knowledge of nonlinear fluctuating hydrodynamics or KPZ or whatever. So we just did numerics here, and pretty much at that point we pretty much stopped. But we didn't analyze too much the line shapes. Question is whether the line shapes satisfy this scaling function. So this is something which we did not analyze too much, and we tried to understand why this is behaving like KPZ, because why is it behaving like 3/2? So why is it resembling Neusy-Burger's equation or KPZ equation? So at that point our understanding was the following. So I'm just presenting this because I don't know if it is useful after all this nonlinear fluctuating hydrodynamics has come up, but I think there is some more things that can be done in this context. So what we did is we basically rewrote this nonlinear Schrodinger equation in this rho and in psi and v variables, and we get these continuity and Euler kind of equations. So yeah. So this term here is exact. It comes from derivatives here, but this term is, as you can see, is irrelevant for us because this is 2 derivatives and this is 3 derivatives in x, which is k cube. And if you have k to the 3/2 behavior, k cube should be irrelevant. So these higher order corrections are irrelevant. but they're not always irrelevant. If you want to study shock waves or solitons, this is a very important term. So for us, it is irrelevant. So I removed this term, and we introduced new variables, v plus minus as v plus square root of rho. So we introduced these, yeah.
You have only 200
Yes, so, okay, so this is a bit more complicated story. So here we are working in a regime of temperature where we actually have two conserved quantities plus one almost conserved quantity. So the number and the energy are conserved, and we work at low enough temperature such that the phase is conserved, the phase difference is conserved. So we work in a regime where there are actually three conserved quantities here. Right, because at low enough temperatures, the peak that corresponds to the heat mode is so suppressed that we try to describe it by effectively two fields. So the right. So I will talk to the. I'll talk about this when I in coming slides. So this is when yeah. So. Yeah.
You're working all this with G positive, right?
Yes.
This is very important, otherwise.
Yes, at the moment this is important, but.
So the third mode he's talking about would be the energy density.
Yes. So in principle, you have two sound peaks and this little heat peak here, but we didn't see it. So when we did the simulation, we didn't see it, and later recently Herbert showed that this is like t times smaller than the other two. So I'll come to this story. This is where I So okay. So here we are saying that these are these two conserved quantities which are good enough to describe what is going on, and then we just wrote down these linear combinations v plus or minus square root of g, and this thing can be rewritten like this. So this thing can be rewritten like this, and so what this is that if you just rewrite it, then on the left hand side you have. So let me just write one of the sectors. So we have dt v plus v plus dx v plus. Okay, I'm just writing the plus part is equal to 1/3 dt plus v plus dx v minus. So in this analysis, notice that we have the first two terms of Neuse-Burgers equation, which is very crucial. So already you see some Neuse-Burgers terms here, and so we basically think of this other sector as acting like a noise and dissipation for the sector of interest. So that was our understanding, that there is this minus sector which is sort of creating noise and dissipation for the plus sector, and effectively integrating this out, you get this dissipation and noise terms, which gives you Neuse-Burgers equation. But to my understanding, no one has actually. It's not easy to integrate effectively in any because this is nonlinear theory. So the idea is that one sector is coupled to the other sector, and it acts like a noise and dissipative agent to the sector of interest. Yeah.
I would expect this is not pure white noise, because since sound now is moving to the left, it's skew the sound noise.
Exactly. So by this logic, it should never be pure white noise. So when you add white noise in fluctuating hydrodynamics, probably one needs to add colored noise actually if you want to. I mean I should. So the point is, yes, if you integrate it out, I wouldn't expect white noise. It should be colored noise. Okay. So this is basically the equations. Right. So then I will quickly move to one page in KPZ. There is nothing much I can add here after the talks already. So this is the KPZ equation: nonlinearity, relaxation, and noise. This is the diagram that you already saw. This is the height, and this height is described by these. The height fluctuations are described by this KPZ equation. The known experiments are burning paper, bacterial growth and liquid crystal interfaces. So surprisingly, there are very few realizations of KPZ physics to my knowledge. So the hope is to add this to the list of KPZ systems. So that is the reason since it is already realized and already measurable, can we add this to this list and put this as a good system to study KPZ physics. This is analogous to this. The structure factor is derivative height correlation. So just to make the connection, and this is 3/2, and the function is also known. The KPZ function is also known. So we have so this is already known, and question is what we get from exact numerics. Is it this function? So, and if you just take extra derivative, you get this noisy Burgers equation. So that's just to show that what I wrote here. If you say that the coarsening dynamics is noisy Burgers, then you basically end up with this, where this is this can be colored, but here is just white noise, and then this is basically KPZ. But the important point is whether this line shape matches the line shape from our exact numerics. And yeah, the line shape matches more or less. This black one is the line shape of KPZ function, and the colored ones are our data for various wave vectors. So the line shape matches. So the question is the exponent matches, the line shape matches, and I didn't talk about it, but there are also some tails which show some KPZ exponents. But the question is now, how do you connect this whole thing to KPZ? And at that point, at the same point, we started seeing how to adapt nonlinear fluctuating hydrodynamics to discrete nonlinear Schrodinger equation. So I will quickly go through the exercise. You start with these equations, you linearize it, and then you get this linear equation. This is exactly in Herbert's notation, but A is now dependent on rho and G. So this is explicit form of A for the nonlinear Schrodinger equation. And then you add noise dissipation by hand, the phenomenological noise and dissipation, and then you compute Hessians, which adds nonlinearity. So basically this is the nonlinear fluctuating hydrodynamics for the nonlinear Schrodinger equation. Okay, so what is this? Okay, sorry. okay. So now we basically linearize it. We linearize this, and you basically create these eigenmodes, phi minus and phi plus, and you see that the diagonal elements are the speed of sound. Okay, so the diagonal elements give you speed of sound, and C is nothing but G rho 0 by m. Okay, so this is so phi are the eigenmodes, and then you rotate the entire nonlinear fluctuating hydrodynamics in use to get the nonlinear fluctuating hydrodynamics for these eigenmodes. So this is basically the expression we get for nonlinear Schrodinger equation, where G's you can calculate explicitly. Okay, so this is the nonlinear Schrodinger. This is the nonlinear hydrodynamics. Now, keeping only the relevant terms. So keeping only the relevant terms, meaning that if I have dt phi plus is equal to, I'm rewriting this, and dx, if I compute this, you see that everything is there here. All the elements of the G matrix are there. Okay, so it will have in principle G phi plus square plus something else phi minus square plus cross terms. It will have everything, but as it was shown in the talk, only this is relevant. Okay, and these are irrelevant. So you keep only phi plus coupled to phi plus, and that gives you your usual KPZ equation. So That's how you get the KPZ equation for nonlinear Schrodinger equation. So when this is there, then this dominates everything else. So if this is not there, then it is tricky. Then more interesting things can happen, and I will talk about this in coming slides. So this is basically what you get. This is the form you would expect, and that is the form that we see. This is the form that we see. Yeah. Okay. Okay. So then, so keep in mind that we had one. Keep in mind that we had one nonlinear Schrodinger equation, and we introduced two fields, rho and v, and from there we created phi plus and phi minus. So we just have two fields. So everything is a 2 by 2 matrix here, and everything is coupled to everything else. So notice that we don't have much freedom here to make things zero. We cannot make this zero, because if we make this zero, some other thing is zero. So it's very hard, and the G matrix is what it is, and the expression also is given clearly. So now the question is, can we realize some more complicated versions of these equations in other systems? So I will skip the next two slides. These are some experimental motivation slides, but because I want to first talk about this, and then I will come back to that if I have time. So now we start with just a multi-component system, and these phi's are just two fields, phi 1 and phi 2. Okay, and this is the general equation that you can write. Okay, this is general coupled KPZ equation that you can write. Okay, dt phi 1 is equal to this, dt phi 2 is also equal to this. So this is a general KPZ equation you can write, and these are the G matrices. And it was shown in this paper and also in yesterday's talk that you will basically have two peaks because you have two fields here, and it can be KPZ, Levy, diffusive, and so on. So question is, in the NLS systems, is there a way to achieve this? So is there some way to achieve this where some terms are forbidden by symmetry? So is there a way to create this, okay, where this is forbidden by symmetry? So can I create something where this is forbidden, which means that I cannot have this and I end up having only some other term? So to do that, we study some coupled NLS equations. So this is like the best I could explain, but this is just very preliminary. So if I have coupled equations, then I basically have two densities, charge and spin density, rho 1 plus rho 2 and rho 1 minus rho 2, and same with velocities. So I have four fields if I have coupled equations. In one I had two fields, in coupled NLS I'll have four fields. Now this is just my charge and spin. So notice that if I take G1 is equal to G2 and background density is same, if I take G1 is somewhere inside here, and if I take the background density is same, then it turns out that the modes are given in this form. The modes, the four normal modes take this form. And these are the four sound velocities. Spin has left moving and right moving sound velocity, and charge has left moving and right moving sound velocity. Now notice that, okay, so notice that, so I have four here, but let me just concentrate on the right moving fields. So phi s plus and phi c plus. So phi c plus can be written as a bunch of terms like this, but phi s plus cannot have phi s square here, because if I switch 1 and 2, if I switch 1 and 2, then phi c goes to phi c and phi s goes to minus phi s. So some terms are actually forbidden because of symmetry, which means that the spin sector can never be KPZ. But the charge sector is KPZ. So charge mode is KPZ and spin is non-KPZ. Probably it is diffusive. Any questions? Yeah. But if I break symmetry, then both can become KPZ. So which means that if I have very symmetric nonlinear Schrodinger equation, then I'll have a spin mode which is non-KPZ and a charge mode which is KPZ. And if I have if I break symmetry, then all the modes become KPZ. So in some sense, you can realize more forms of this, more forms that are shown in this paper, more combinations of G's. So that is the thing, and so this is so now these are some very preliminary data that I have, which I don't really understand. This is basically what I showed. This is the line shape for discrete nonlinear Schrodinger equation when the lattice spacing is finite. When I make lattice spacing smaller and smaller and do the same computations, the computations become much harder and harder. It turns out that my exponent goes from 3/2 to 1, but still everything collapses into a scaling form. So it seems that there's a nice scaling form, but the scaling exponent goes to 1, which means that it is hitting some integrable like regime, which you expect, but so basically here you're trying to study what happens in that crossover between discreteness and continuum, between non-integrable and integrable. So, but this is not of KPZ scaling form, and probably it is not universal, but I don't know any other model where I have not seen any other plot yet. So there is probably some data on Toda lattice, but this is the NLS. For NLS we have seen this. So basically what I wanted to say is that, yeah, any question? So what I wanted to say is that the discrete NLS, the story is slightly more complicated that I presented here. I am studying in a very specific regime in temperature. So if this is temperature, I am in some specific regime here, okay, where there are 3 conserved quantities. Okay, there is 3 conserved quantities, and there is this additional velocity field that is acting like a conserved quantity. And there is a regime here which is high temperature regime where there is only 2 conserved quantities, the energy and particle number, and here there are 3 conserved. And if you keep on reducing the temperature, you actually see in a recent paper by Herbert that you actually see some non-integrable structures emerging even for finite lattice spacing. But I just wanted to point out that I'm studying in this very specific regime where what I would expect is 2 KPZ peaks and 1 little heat peak. And since we didn't see this, we sort of tried to write this simplified model to explain this and this. So to conclude, so the blue is in conclusions and red is future. In discrete NLS, we studied nonlinear fluctuating hydrodynamics and KPZ. Line shapes are universal, which is not, and they are not model dependent. We studied exponents. Nonlinearities are clearly crucial, and this is an ideal platform to probe dynamical critical phenomena, and will serve as future testbed for KPZ physics. For the vector NLS, namely multi-component NLS, we showed that you can get multi-component noisy Burgers equation of a more variety, and you probably have more classes because you have more knobs to tune, and you see crossovers or some symmetry breaking features from KPZ to diffusive and so on. So this is some things which we just outlined. These are questions which I don't know answers to, but they're interesting questions. What happens if you add terms which are not Hamiltonian-like, and what happens to universality for such systems? Do we still have KPZ and so on? So this is also another thing that I just explained briefly, that you have a high temperature regime and a low temperature regime and an ultra low temperature regime. But for this, there is a recent paper by Herbert which has everything. So there is also very interesting to study non-local versions of NLS, because all the conjectures and results about fluctuating hydrodynamics and models falling into KPZ are typically for local systems. But there is clearly a non-local systems where technically we have a lot of things that we can handle. So it's easy to ask these questions for non-local systems, whether you have KPZ or some other kind of universality class. And just a reminder that even 2 dimension is still anomalous, but there are no works on 2 space dimensional versions of this system. So what happens to exact numerics, and can there be some mapping to like 2D versions of KPZ and so on? So thank you for your attention.
Could one imagine any experiments on cold atoms where this KPZ behavior could be seen?
So in cold atoms, they can realize 1D Bose gas. So they can realize a bosonic gas which behaves like nonlinear Schrodinger equation. And although the continuum version is integrable, the experiment is sufficiently bad so that it is basically non-integrable. So the system is realized. There is a measurement that can calculate this S of k omega. But to my understanding, nobody has measured this in this specific regime of temperatures. So there is some measurements on in some other regime, but it is possible. In cold atoms, it is definitely possible. Yeah.
Can you make it 1D?
Yes. You can make the confinement so hard in one of these things. So basically, it's a cigar-shaped trap typically, but you make it radially confine it so strong that you can get typically like more or less 1D. So yeah.
There is like calculations of like equilibrium conditions in quantum, which probably is more relevant for cold atom.
So at finite temperature, I don't know. At finite temperature, dynamical structure factor for a quantum system, I think not. But 0 temperature, there are some calculations. But finite temperature, I don't know. I think not. If there's anyone who knows anything else, please correct me. But I don't know any calculation, any theoretical calculation. So presumably you want to do Bose-Hubbard model. Yeah. You want to do Bose-Hubbard model. So. Yeah.
So do you have some information about the exact temperature for which you have the crossover?
Sorry?
So do you have some information about the temperature for which you have the crossover?
Oh, okay. So there is this 3 temperatures, right? So there is. Oh, sorry, that was already good. So this temperature, there are some estimates, but I don't really understand it very well. So there is some estimate where if you increasing temperature, then the pseudo-conserved quantity will stop getting conserved. Then you start having vortices and so on. So there is some estimate, but I don't understand how you get those estimates. So I think the estimate is something like the temperature, inverse temperature should be like G rho tilde or something like this. So I don't know. So the thing is that if you wait long enough, I think everything should start going this direction. So if it also depends on time. If you start waiting for long enough times, then even if you start from low temperature, if you keep waiting for long times, then the quantity which was conserved will stop getting conserved, and then you may hit diffusive regime. So I don't know how to estimate this temperature properly.
And you don't have any conjecture about what happens exactly at this temperature?
At this temperature?
Exactly, at this one. Do you have?
No. So no. I mean, I basically work in this regime. And I also did not, basically I never worked in this regime, but I remember having high temperature results, and later there was actually a full-fledged paper which had diffusive behavior shown here. But when we tried to get KPZ, we tried to just look for KPZ. So when we didn't get KPZ, we reduced the temperature. So we didn't want to go here. But now there is some recent work. So, but I don't know. Yeah. Can you say anything, Herbert?
It's an active. It's an activated process, right? I mean, so you know, the crossover will be reasonably sharp, but it's not really any sharp transition. So yeah, that's right. It depends on what you measure.
But you could expect some new universality class at this point, or not?
Not really, because it's really more like a crossover in the sense that, you know, I mean, you know, you have this extra conserved quantity. Now, let's say it's not really conserved. It's 99% conserved, and then if I go to somewhat higher temperature, then it's only, you know, then it's only 50% preserved, right? I mean, so there, I don't think there's a really very specified point where you could see. There's no really well specified point where you could see, you know, saying that I like a critical point, and then you could sort of ask yourself what are the properties at this critical point.
I just, one question, which I think is related to what you're asking, is the crossover universal, right? Is there just one parameter, some one parameter scaling that gives you the crossover from KPZ to diffusive?
Right.
I think that's the interesting question, right? If it really is a universal crossover, you know, then you can treat both regimes in one framework. And I think that is a possibility. But this is, I think this is still open, right?
Right.
Thank you very much.